solutions of the Einstein equations coupled to any matter I will not define what I mean by almost. The only solutions are the Kerr-Newman solutions. If there is one black hole. That means that if you want to study black hole spacetimes, all you need to do is study the Kerr-Newman solutions, and you don't need to study anything else. Now, this is obviously a powerful theorem and one that is quite complicated to prove. Therefore, I will not attempt to prove it. But what I will do is to show you a way of proving a restricted version of this theorem, largely because all other versions of this theorem work in exactly the same way. They just get progressively more and more complicated. So the style of the proof is more important than the technical details of it. And the simple thing that I'm going to do is to look at static solutions of the Einstein equations coupled to a scalar field. Let's call the scalar field phi. And I'm going to impose asymptotic flatness. I'm going to have a single black hole and I'm going to prove that there is no scalar field. So this is an important step in the proof of this kind of uniqueness theorem. You might imagine that a black hole, because it can act as a source of an electromagnetic field, could just as well act as a source of a scalar field. That turns out to be false. Similarly, you might expect a black hole to act as a source of a large quantity of other fields with their associated physical properties, but that also turns out to be untrue. It gets harder to deal with stationary spacetimes as opposed to static spacetimes, but I wanted to look at this particular case because it is relatively straightforward and illustrates the general point. So let's consider first of all the metric, given that we know that there is a static spacetime that is asymptotically flat. Well, the space-time you want to think of as being a four-dimensional metric, but you can, of course, fix surfaces of constant time, constant t, because the thing is static. And any one surface will be the same as any other surface. By static, I mean, technically speaking, that there will be a killing vector let's call it Ka, corresponding to time translations. So that Ka d by dxa is equal to d by dt. That means that it is possible to choose a coordinate system in which the metric takes the following form. ds squared is equal to minus v dt squared plus some spatial metric. You'll notice that because this Killing vector k corresponds to time translation, k must be a time-like Killing vector. So that, at least if you're away from the horizon, v is positive. Furthermore, since the metric is asymptotically flat, you know that there will be a set of coordinates in which this tends to flat space at spatial infinity. And equally well, v has got to tend to 1. Then there is the issue of the horizon. Well, the horizon is a surface, presumed spherical. You can actually prove that it has to be spherical in dimension 4. So this surface you want to think of as being R3 minus whatever you have sitting here, where this surface is going to be the horizon. So this is minus a disk. The horizon has topology of being a two-sphere, although it doesn't really matter that it's a two-sphere for what we're going to do. On this surface, the Killing vector k must become null. To see that that is true, what you just do is to think about how this thing evolves in time.
We're starting to use the assumption that we have a single black hole. Is the reason why that is a necessary caveat is because you could have like two extremal black holes? That
Yes. For this thing, yes. Okay. Yeah, exactly. It's interesting as to why it doesn't work. Okay. The thing which makes it not work is the fact that it's degenerate, that they have these degenerate horizons.
Asymptotically, if you're out of infinity, can you tell the difference between a solution with a dipole of maximal extremal black holes relative compared to like just to work in?
You mean, could you tell the difference by some local measurement you had two as opposed to one big one?
Yeah.
Depends how hard you're willing to look. If all you do is to probe the leading order fields so that you look in the Newtonian approximation, you'll see the mass if you probe the gravitational field, and you'll find the charge if you probe the electric field, and you won't find anything else. But you will find higher order multipolar moments if you look harder.
Yeah, we find a dipole.
So you would find a dipole, electric, and you'd find all kinds of strange things in the gravitational field too. But it's not the thing you'd notice first. That's why I say you'd have to look hard. Oh yes, so I was going to try and draw a picture to convince you that the Killing vector was null on the horizon. Well, here is one surface of constant time and here is another. The metric on these surfaces is of course the same, and if you just consider what happens to the horizon, well, it's got to look like some cylinder which stretches between the two. And you know that light cones must have tipped over to look something like this. So an example of time translation which leads you where you are, simply moving up the horizon. So that thing, that vector is tangent to d by dt. It moves you along the horizon but the horizon is defined to be where there's a light ray. So that's enough to tell you that V is equal to 0 on the horizon. Now we have to ask ourselves about the scalar field. The scalar field phi will have equation of motion. Let's make it a free scalar field so that we don't get confused. Box minus m squared phi. So it obeys the Klein-Gordon equation. And if you ask about the action that's associated with that, you would say, oh, it was minus 1/2 grad phi squared minus 1/2 m squared phi squared g to the half d4x. And if you calculate the energy momentum tensor from this by the standard kind of technique, you will end up with the energy momentum tensor is equal to del A phi del B phi minus 1/2 GAB of grad phi squared. And so you need to solve the Einstein equations, being RAB minus 1/2 R of GAB is equal to 8 pi times TAB.
Why does phi satisfy the Klein-Gordon?
All Lagrange equations from this. Why did I make it do that? Why didn't I have phi to the 4 or some such thing? Well, in actual fact, I could put in a phi to the 4 with lambda positive, and it wouldn't make any difference. If I put in a phi to the 4 with lambda negative, as you would do for a Higgs field, then life will become rather more complicated. I did this to make life easy for us. So you're always free to make it more complicated for yourself if you wish, but the basic point is can be seen by doing something relatively simple. That's the real reason. So it was a choice.
The theorem goes through with arbitrary couplings?
Well, if I start expanding about unstable points, as I would do if I did Einstein-Higgs or something like that, then you can get yourself into a certain amount of trouble. But if you're sitting at the bottom of the potential, if it was a Higgs potential, you'd be fine.
Okay.
There are some subtleties about Yang-Mills fields, which I absolutely don't want to go into. Now, so what are the conditions on phi? Because the space-time is asymptotically flat, you know you can't have too much energy momentum out at spatial infinity. And so phi has got to die off. So that means that you know that on general grounds that phi has got to look something like e to the minus mr over r at infinity, or dies off faster. You can find solutions which blow up as r goes to infinity, but we're going to assume that we're just not interested in those. So that's the boundary condition at infinity. Now what you do is you just think of an integral identity. The easiest one to think of here is to take the wave equation, box minus m squared phi, multiply it by phi, and integrate over g to the half d4x. That being some region of space-time, it may as well be this region. So we could integrate over this thing between these two spatial sections where t is constant. This must be equal to 0 because the field satisfies the Klein-Gordon equation. Now what you do, so we've integrated over this thing. Now what you do is you just integrate by parts. So if you integrate by parts, phi box phi becomes grad phi squared with a minus sign minus m squared phi squared g to the half d4x integrated over the same domain. This has got to be equal to the integral over all boundaries of phi del I phi d sigma I, where this is the volume element on the boundary, meaning ni d sigma, this thing being the unit outward normal to the surface. And it does not matter whether that's a time-like surface or a space-like surface. What are the boundaries of M? Well, the boundaries of M, you see, are going to come in 4 different types. You can think of the boundary of M containing 4 components. We've drawn it here. There is one of these space-like surfaces in the past and one of these space-like surfaces in the future. So there's the initial space-like surface, and the final space-like surface. I guess I should emphasize one further point. Because I'm interested in a static space-time, I've got to choose a phi that is independent of time. If phi, of course, depended on time, its back reaction on the metric would make the metric depend on time. So that means the geometry here and the scalar field here is the same as the geometry here and the scalar field here. A unit outward normal looks like this on this surface, but looks like that on that surface, so the two things will cancel. Now let's consider what happens at infinity. Out at infinity, you know that phi, at least as long as m is not equal to 0, is dying off exponentially, or faster. Given that, we can contemplate evaluating this integral over a surface at constant r somewhere near infinity. D sigma I looks like a unit vector in the normal direction, let's call that ni, times the surface area element, which has got to look like dt sine theta d theta d phi times r squared. And this vector will look something like 0, 1, 0, 0 in t r theta phi coordinates. So, since phi is dying off exponentially, and this is a power, that's enough to convince us that you get no contribution from infinity. Lastly, there is a component of the boundary on the horizon. That's this cylindrical tube here.
What sense is that a boundary? What sense is that a boundary?
I can decide to integrate over anything that I want, so I decided to integrate over that as a boundary.
So you find out essentially.
Well, now let's think about what's actually happening on the boundary. We are trying to integrate phi grad phi d sigma I over this boundary. So let's make this a vector bi to be phi del I phi. D sigma I is the unit normal to that thing times some scalar. And what we're interested in is bini, that quantity. That's what we want to integrate over this surface corresponding to the horizon. But by the Cauchy-Schwarz inequality, the square modulus of this must be less than or equal to bi times ni. But ni is null on the horizon. So this thing is equal to 0. That tells you that this thing is equal to 0. So no boundary terms give you any contribution whatsoever. So what you have got now is slightly different, that the integral over m of minus grad phi squared minus m squared phi squared g to the half d4x is equal to 0. Phi does not depend on time. So if I use my form of the metric here, there's no t term in this, so this really reads minus di phi dj phi hij minus m squared phi squared d4 g to the half d4x. Now let's think back to the metric. I think we've erased the metric, so let's reinstate it. Inside m, v, remember, is positive. So the only time-like direction is t. Since the metric must have signature minus plus plus plus, it follows that this part of the metric must have signature plus plus plus. In other words, hij is a positive definite object. If you diagonalize it, it would only have positive eigenvalues at each point. Therefore, hij contracted with any vector whatsoever must be positive, or 0 for all x. Consequence is that this term here is of definite sign, it's always negative. And this term here is of definite sign and is always negative. So the expression here is negative semi-definite. And it will be 0 if and only if phi equals 0. So you've shown that the scalar field has got to vanish, and therefore you can have no black hole solutions that act as sources of a scalar field.
This realization of the argument, I don't think we made use of the fact that there's only one. I mean, if we would have...
I haven't used it.
If we had 2 or 3 black holes, it wouldn't have made any difference.
No.
Yeah.
Not for this case, but it would for the uniqueness theorem as stated earlier. It better had to, because we already know of a counterexample.
Yeah.
Why is the normal to the horizon null? Because can't you take a space-like normal to the horizon?
So what you're asking is about the surface R equals constant, and I think you'll discover that that thing is null. There is, of course, a let out. It might be that m is equal to 0. Then phi equals constant. And you can have such a thing. But of course, if phi is constant and m is equal to 0, TAB is equal to 0. All other uniqueness theorems work in exactly the same way, so I am not going to pursue them, but merely refer you to a place where you can find it all written out if you absolutely need to. And that is a book entitled Black Hole Uniqueness Theorems. By M. Heusler. It's possible that Professor Gibbons in his course will give you some more insight into that particular problem. So what I want to now do is to go and look at some properties of the Kerr-Newman sequence of solutions. A bit more explicitly. For most of the time you don't actually need to do horrible calculations using them, but it's worth remembering or having in mind what the metric looks like. So the metric is r squared plus a squared cos squared theta into dr squared over r squared minus 2mr plus a squared plus q squared plus d theta squared plus 1 over r squared plus a squared cos squared theta into. I'll write it in a slightly different form. Minus. So I've just collected up terms here. That's the only difference between what we wrote out now and what we're writing out now. Again, I'm not going to expect you to remember this, but I don't want you to come away thinking that this thing is completely and utterly unfamiliar. So, we have to do a small number of calculations with this. And explore a certain amount of its properties. So the first thing is that the Kerr-Newman sequence of solutions is characterized by having two killing vectors. I mean, they're all asymptotically flat, that we take as read. They all have two killing vectors, which will play a role in what we're going to do next. One is a time translation killing vector, let's call that T. it has the property that TA d by dxa is d by dt. So in these coordinates over here, TA has the explicit realization 1, 0, 0, 0. It moves you forwards in time. There is a second killing vector associated with the fact that this thing has axisymmetry, so it's usually called a rotational killing vector. RA, is RA d by dxa is d by d phi. In the same language, this is 0, 0, 0, 1, and this is associated with the fact that the thing is axisymmetric. The horizon, you may recall, is the surface where r squared minus 2mr plus a squared plus q squared is equal to 0. Now, if we think about some properties of this, well, you probably want to think about it in this kind of way. You want to think of the black hole as being some isolated blob, perhaps just like a liquid drop or something, sitting in space. So phi represents rotations about some axis that looks like that. The thing is rotating. This is going to be the horizon. And so d by d phi represents rotations around here, and this is a surface where r squared minus 2mr plus a squared plus q squared is 0.
In arbitrary dimensions, does the Kerr-Newman solution, do the two horizons intersect on S1, S0? I mean, just at 2 points, or does it intersect on other?
Wait a minute. In dimensions other than 4,
Yeah, higher dimensions.
in dimensions 5, something goes wrong with the uniqueness theorems. So,
Yeah, but let's just say we have a rotating black hole.
a single rotating black hole.
Yeah.
Yes.
I'm looking at the two horizons, which are now not two spheres.
Oh, the inside and the outside,
Yeah.
you mean? Yes.
Do they intersect on one sphere or on a zero sphere?
I guess I should know the answer to that. I think it depends on what you've done with the rotation parameters.
Okay.
That's because in dimension 5, instead of having one rotation parameter, you have two rotation parameters. That's because the group of rotations is SO4 and not SO3, and that's got two Casimir operators, not one.
It should be a circle then.
Well,
Unless they overlap.
Well, that's the point. I think that they can overlap for various things. Yeah. I don't think that the global structure of those has been fully explored,
Okay.
even though
Okay.
even though they were invented close to me. And the uniqueness theorems do not work because although in dimension 5 you can have spherical black holes like these, you can also have black rings where the horizon, instead of being a 3 sphere, is an S1 cross an S2. Very exotic. And who knows about dimensions more than 5. And even in dimension 5 you don't know you can't have S1 cubed. However,
Wait, you mean they still don't know that today?
no.
Okay.
However, the horizon must be generated by a killing vector, which is null. Meaning tangent to it. A quick inspection of T and R will reveal that neither T nor R is null on the horizon. So what will happen in general is that there will be a killing vector Ka, which is some linear combination of T and R which is null on the horizon. After all, remember that if you have two killing vectors, you can always find a third one by taking a linear combination of the two. So here is a linear combination. This thing will be null on the horizon. If you want this thing to be a killing vector, it better be the case that omega is a constant. And if you think about not writing it this way, but writing it in a sort of using that notation, Ka d by dxa that's going to be, from what we've got sitting up there, d by dt plus omega d by dr. So what that tells you is that omega is an angular velocity. And to all intents and purposes, you can use this to define what you mean by the angular velocity of the black hole. It's a definition of what you mean.
D by d pi.
Phi, thank you, yes. It's R for rotation. Now, of course, you need to calculate omega from the knowledge of what t is and what r is and the metric. It's not completely impossible. And in fact, all you need to do is to say, well, Ka must be 0 on the horizon. So that tells you that Ta plus 2 omega Ta Ra plus omega squared Ra must be 0 on the horizon. I can evaluate this from knowing what R is and the metric, this from knowing what T and R is and the metric, and this from knowing what T is and the metric, and evaluate it on the horizon. Of course, that's not so easy because this is a rather unpleasant mess. So, on the outer horizon, which is the only one we're interested in, R equals R plus, which is equal to m plus the square root of m squared minus a squared minus q squared, you discover that omega is equal to m, can't be, a, divided by 2m squared minus q squared plus 2m times the square root of m squared minus a squared minus q squared. So that is referred to as the angular velocity of the black hole. Now, the way I've done this, you know that the following result had to be true. But, in fact, the way it was originally done did not encompass this fact. So, here you have the black hole that looks something like this. Lots of things depend on theta, which is the colatitude out to some particular point that looks like that. It might have been that omega turned out to depend on theta. That is to say, the angular velocity of different parts of the horizon was different. That could have happened, but obviously did not happen. I just want to draw that particular fact to your attention. So omega is constant on the horizon, meaning it is not dependent on theta.
is constant, but that just means it's constantly tight.
No, it's actually got to be a constant if you want this thing to be a killing vector. That's why I said that in this particular way of doing it, it is necessarily the case that omega was a constant. But I want to draw your attention to the fact that it is indeed independent of the value of theta that you've picked. There are other ways of defining omega where this happens and looks like an accident. I think it's not an accident, I think it's inevitable. However, the next quantity that I want to look at is also independent of theta. So, let's go back to our description of K. K, we know, is a killing vector, and it is null on the horizon. Now, if we think about what we mean by the horizon, it's a surface that looks like this. And if you ask about light rays can move up the horizon and stay where they are, because the light cones look like this. So this thing must be geodesic. So it must obey the geodesic equation on the horizon. That's because the horizon represents light rays that are moving outwards as fast as possible, as rapid, but you know what I mean. Let's contemplate the consequences of that. Well, it means that K is null and will obey the obey the geodesic equation on the horizon. So on H, K is null. We already know it obeys the killing equation everywhere. But on the horizon it must be null, and it must obey the geodesic equation. That reads Ka del A Kb. You might be inclined to say this has got to be equal to 0. But it is not true. It just has to be parallel to Kb. Remember that this would be 0 if and only if you could write it in that form as an exact differential, then u would be an affine parameter. But nobody said that this k had to be affinely parameterized, and in general it won't be. So there will be some coefficient, kappa, which sits in front of k. Remember, the geodesic equation says Ka del A Kb is proportional to Kb. So here is a quantity kappa, which might be 0, but might, if it's affinely parameterized, would be 0, but is not necessarily 0. This thing has got dimensions of 1 over length. That's kind of obvious because k is dimensionless and del has got dimensions of 1 over length. Something with dimensions 1 over length in my units has got the same dimensions as acceleration. Length over time squared is the same as length over length squared because c is 1, which is 1 over length. So this looks like an acceleration. It is usually referred to as the surface gravity of the black hole. So that's a definition of it. Obviously, it looks like evaluating a kappa is going to be a bit involved. but there's a sneaky way of doing it that is not as involved as you might imagine. You have to be kind of careful with this, though. The easy way to do it is to start off, I should say that usually you take kappa to be positive, in which case there could be a plus or minus sign there. So, if you take this formula and square it, you will of course end up with, I don't want to do that yet. Let's start off with this relationship. From the Killing equation I can turn this round and write this as minus Ka del B Ka equals that. And if you think about it, that's the same thing as, this is all evaluated on the horizon. Now what you do is square it. You will get a quarter. Now, Ka, I can just call the norm of the Killing vector. Let's write it as V. So this thing reads a quarter of grad V squared is equal to plus or minus squared, kappa squared, KB, so it's equal to a V again. So I end up with some formula that looks like that. And often, it is the easiest way to calculate it is to start from that result. I guess we have to stop there. I will do that explicitly for Schwarzschild and tell you the answer for Kerr-Newman on Friday. So let's stop there. There is a problem sheet here if you have not got one, but to find it somewhere.